19 million years ago, a lineage of fruiting plants in the Solanaceae family experienced a divergence. One of these emergent lineages would go on to become the chili peppers of the genus Capsicum. This is named after capsaicin, or capsaicinoids, which are secondary metabolites produced by the pepper, which give them their heat, or their spiciness. The other lineage that formed out of this divergence, the genus Solanum, would go on to produce tomatoes. Tomatoes, quite unlike their chili pepper cousins, don't express capsaicin. They have a much milder taste, with a softer, wetter texture. Recently, researchers discovered that, thanks to its close relation to the chili pepper, the humble tomato possesses all of the genes necessary to produce capsaicin. The tomato has the genes to maintain the capsaicinoid biosynthetic pathway, but most of these genes are infrequently expressed, and some of them, like the CS gene and the BCAT gene, aren't expressed at all. The researchers determined that it will take the relatively simple effort of modulating the tomato's gene expression to get it to express these genes at the desired levels, so as to produce capsaicin, and give tomatoes a spicy kick. The first strategy they suggest is to use the genes for bacterial proteins called transcriptional activator-like effectors, pack those genes into a viral vector, and then use this to upregulate the expression of critical capsaicin genes like the PAL, the KAS, the COMT, and the FATA genes. Furthermore, they found that the CAMYB31 transcription factor can upregulate most of these genes as well, so activating that gene could express a lot of the other genes and do a lot of the work for them. The second strategy involves the installation of promoters into the tomato's DNA. By inserting specific promoter regions at strategic points in the tomato's DNA, they can get the tomato to naturally express these genes in the course of its normal gene expression, in the course of its normal transcription. It would be like the workers in a company having a daily routine, and the boss adds a few more tasks onto the daily routine, and they start getting done every day along with all of the other normal tasks. Even though they offer these suggested strategies, the researchers also express a healthy skepticism about these suggested strategies. They say, quote, "It remains to be determined, however, if the products of these genes are fully functional, biochemically active, and catalyze the appropriate reactions," unquote. Alright, so what would be the purpose of this? What's the point of genetically modifying some tomatoes to make them spicy like chili peppers? The researchers explained that the benefits would be mostly economic and almost entirely confined to the food industry. They explained that chili peppers are finicky plants. They're sensitive to the environment, and they tend to produce inconsistent, variable levels of capsaicin, which makes it difficult to grow consistently spicy peppers. Consistency is important in agriculture and in business, and if you have a crop plant that is sensitive and grows inconsistently, that makes things a little difficult. Now, in contrast, you have tomatoes, which are relatively easy to grow. They're a lot less sensitive to environmental stresses, and they could theoretically produce more consistent levels of capsaicin. Thus, they could be turned into an agricultural product with a consistent, controllable level of spiciness. The agricultural and economic possibilities are obvious. First of all, tomatoes are healthy, and capsaicinoids have health benefits of their own, so all of this in one package could make for a particularly healthy food, and that's great. Also, these modified tomatoes could be used as substitutes for regular tomatoes in virtually any food that you can think of that uses tomatoes. Imagine pizza with a spicy sauce, or imagine a salad with zesty tomato pieces, or imagine sandwiches with tomato slices that add an extra kick. The scientists also think that they could alter some of these genes to modify the chemical pathways to produce entirely different chemicals. For example, lycopene is a precursor molecule that exists in tomatoes. It naturally exists in them. But chemical pathways could be altered so that this lycopene is metabolized into the antioxidant beta-carotene, or the color additive bixin, among other possible chemicals. As you can tell, there's a lot of potential here, and it's really interesting, and it's really fun to see how this science is being used to customize our foods, for taste, for nutrition, and for all sorts of other stuff.